Hello students, welcome to Fatigue Analysis for Extreme Environments. I'm Dr. Stewart. Today we're going to learn about how to apply the stress life approach for notches. Stress concentration factors such as KT and KTS are often found using quasi-static conditions, meaning we're loading at a very slow rate. So we can say that these are static loading conditions. It's important to note that some materials, when fatigued, are not fully sensitive to the presence of notches. And so during fatigue, their KT values are reduced. For these materials, we introduce a new factor called the fatigue stress concentration factor, KF and KFS, which describe the relationship between the smooth fatigue strength, so the smooth fatigue endurance limit, divided by the notched fatigue strength, the notched endurance limit, right? And this value, KF, is bounded between 1 and the value of KT, where it is less than KT, but greater than 1. Now, the effect of a notch is accounted for in the same manner as it would for a smooth specimen, where KF is the endurance limit of the unnotched over the notched, and where that notched endurance limit would be equal to the endurance limit, including all of the Marin factors, all the modifiers, due to load, surface, size, and other miscellaneous effects. It's also important to note that KF, this factor, is dependent on material type. Unlike the static factor, which is based on geometry and loading, KF also is sensitive to material type. Now, how do we actually account for this modification? How do we introduce or define this KF factor? What we do is we introduce a new factor called the notch sensitivity factor, Q, which is empirically determined and describes the relationship between material type and geometry. Now, this Q, notch sensitivity factor, is equal to the KF, the fatigue stress concentration factor, minus 1, divided by the static stress concentration factor, KT, minus 1. And we can rearrange that to come up with a calculation of KF, where KF is equal to 1 plus Q times, in brackets, KT minus 1, right? So this equation here. We also would have a companion version for when we're under shear loading conditions, where we have a QS and of course, a KFS. Now, this notch sensitivity factor Q is empirically determined, meaning after many experiments of different materials, we're able to define what its value is. This here is an example that shows the notch sensitivity factor as a function of geometry. So see here on the x-axis the knot root radius, as well as material type, where the lines define different types of materials. The solid line are different steels with different values of tensile strength, right? And the dotted line is aluminum alloys in general, right? So what we would do is we would generate this notch sensitivity factor chart. We would design our geometry and do our material selection, and then we would be able to define what is the Q factor that's related to both our geometry and material. Now, there is another factor that we can use to define the relationship between geometry and such to get our fatigue factor. Neuber developed the following approximation for the notch factor where we have a fully reversed fatigue cycling, where R is equal to -1. The relationship is that Q is equal to 1 divided by 1 plus the square root of rho divided by R, where R is the radius of our notch root, and the square root of rho, that is our characteristic length that's dependent on the material. Now, this relationship could be rearranged or defined in terms of KF as follows, where the KF, the fatigue stress concentration factor, is equal to 1 plus KT minus 1 divided by 1 plus the square root of rho over R, right? Now, values of this characteristic length, the term, the square root of rho, for steels are shown in the figure here to the right, where it shows the relationship between the tensile strength and how that characteristic length changes, and then ultimately will affect our fatigue properties, right? Our fatigue stress concentration factors. In addition, we have here a table of some characteristic lengths for aluminum alloys. There is a third parameter that we can use to describe the relationship between the static and fatigue stress concentration factor, and that is the one developed by Peterson. Yes, and this is the same Peterson from stress concentrations themselves, from the Peterson stress concentration factor handbook. Peterson observed a good approximation of the fully reversed fatigue loading can be obtained using a similar formula to what was previously found, where here instead we have Q, the notch sensitivity, is equal to 1 divided by 1 plus A over R, where A is another material characteristic length, and that can also be defined in terms of KF and KT, and where the values of that characteristic length A can be estimated for different materials. Here is an equation for steels, and metric and English units, and as well for aluminum, a good estimate is a single constant value of 0.635 millimeters. The formulas to estimate our fatigue stress concentration factor, whether it's using notch sensitivity, which is Q, or Nueber's, which is the square root of rho, or Peterson's rule, which is the A parameter, all of these methods are empirical in nature, meaning they're derived from the results of many experiments. In general, we find that hard materials are usually more notch sensitive than softer materials. Now, in the absence of real data on the behavior of notch parts, we must try to come up with a way to estimate those impacts. And there are two approaches that are typically used. One is the Hayward model, the other is the Collins model. In the Hayward model, what we do is we would plot our stress life data, a line which is a solid line representing our smooth material behavior, and another line representing how much our factor, our endurance limit, has been degraded by the presence of a notch. In the Hayward model, what we do to make predictions is we shift this notched line down, and we use the S1000 point, the equivalent S1000 point of the notch specimen, in order to make our predictions. So in order to get our A and B parameter for the stress life approach. In the Collins model, it's a bit simpler. Rather than using that S1000 location, we go ahead and use one cycle, 10 to the 0, as our point of pivot. And so, of course, the Collins model is simpler to use, but it is less accurate over our low cycle fatigue range. So now, a stress life curve for a fully reversed part that also has a notch can be resolved if we have the following information. One, if we have some monotonic data, the ultimate tensile strength or the true fracture strength. Two is if we have the fatigue strength for our smooth specimen of comparable size. Three is if we have the characteristic length values, either A or rho. And four would be the elastic stress concentration factor, the KT, and the radius of the notch. If we have these four categories of data, we can go ahead and draw that stress life curve. So let's look at an example of how to do that. In this example, we have a 80 millimeter wide sheet of 1020 hot rolled steel. It has a 10 millimeter center hole, and we're asked to construct the stress life curve for this notched component using the Collins model, using the model where we assume our pivot point is at 1 cycle. Let's start our solution with finding the properties of this 1020 hot rolled steel. In the book, we would go to table A.1 and we'd find our endurance limit, SE, is equal to 241 megapascal, which is associated with 10 to the 6 cycles. Our ultimate tensile strength for this material is 448 megapascal. And what we want to do is we want to define the smooth line, define the line from 448 megapascal in 1 cycle to that endurance limit of 241 megapascal. So let's go about doing that. Start there. After we do that, we then want to consult for this specific geometry the stress concentration factor chart and find the KT value. In our book, we would pull from figure 7.1 that's specific to this geometry and loading condition, and we'll find that our static stress concentration factor, KT, is 2.7. Next, we would go and find our Neuber chart, which is figure 7.7, and take our dimensions here, and we would find the characteristic length is 0.24 millimeters. Then we'll take Neuber's equation and find the Kf, this fatigue stress concentration factor, as 2.4. Finally, we can put all of that together and plot our stress life curve. Where our first stress life curve represents the curve for the smooth component. This is actually where Kf is equal to 1, so that means this would be the smooth specimen. And then our second one is where we apply that Kf factor of 2.4 that we calculated. And this represents the stress life curve of the notched specimen. It should be noted that for materials behaving in a brittle manner, the notch effect at short lives is usually more pronounced than this solution. And an alternative estimate of the stress life curve for a notched member made of a ductile material assumes equal fatigue strength of the notched and smooth specimens. But let's learn more about that as we move forward. Now let's get into a new concept, and that is, for the stress life approach, how does mean stress have an influence? Mean stress influences the fatigue stress concentration factor. It has an influence on the Kf that we find. If we were to conduct many experiments on a material, in this diagram we're looking at a constant life diagram of a 7075 T6 wrought aluminum. If we conducted many experiments for both smooth as well as notched specimen, and these experiments were done with different values of mean stress, as well as different values of stress amplitude, we'll see interesting behavior. In one case, the first case here is the case of 0 mean stress, right? The mean stress is equal to 0. And what we'll find if we are relating, this is real data, where the solid lines are data from smooth experiments, the dotted lines is data from notched experiments, we'll see that the calculated from experimental data Kfs at a 0 mean stress are in the range of 2.3 to 2.2, right? And this is at 2 different locations, 2 different numbers of cycles, from 10 to the 4 cycles, it's 1 set, and 10 to the 7 cycles, which is more representative of the endurance limit, right? Now, let's look at another case. Let's look at the case where we actually introduce some value of mean stress, this line. And that mean stress is 172 megapascal. Well, when we calculate our KF factors with the presence of mean stress, we see these KF factors are much larger. The KF at 10 to the 4 cycles is 3.2. The KF at 10 to the 7 cycles is 5.7. So it's clear from this diagram and from the evolution of these lines that our fatigue stress concentration factor, it changes with mean stress. Now, one way for us to try to account for the combined effect of mean stresses and the presence of notches is to construct the Haig diagram. The Haig diagram is basically a diagram where we take the results of many experiments and define graphically the relationship between notched and smooth specimen with different values of mean stress and stress amplitude. It's a fairly complicated plot that requires several points, several experimental points to craft. An alternative method, which is more convenient, is to apply modified Goodman's equation, which is written in a number of ways, but we're going to show it in this following method, where KF times the stress amplitude SA divided by SE notched plus KFM times SM net over SU is equal to 1. SA and SM, those are the net alternating and mean stresses. So the net stress amplitude and mean stresses in our fatigue cycles. SU is the tensile strength of our material, and SE notch, that is the notched fatigue strength of the material. And an important thing for us to note is that this KFM here with mean stress, because we know that mean stress has an effect on KF, we're going to say this KFM depends on the material type. And we would define those two types as either ductile or brittle. For ductile material, Dowling has defined the following inequality that depends on the elastic plastic state in the material. If we're not yielding, then KFM is equal to KF. If we do have some value of yielding, then KFM is going to be kind of an evolving term. Where if we're under reverse yielding, we're at KFM is 0. And if we want a conservative estimate of the initial yielding within our material, we would set KFM equal to 1. For brittle materials, we would define KFM as equal to our KF, and we wouldn't have to do anything special. Now, the other approach we have is that modified Goodman equation. Modified Goodman is very convenient, and we also can create a graphical version of modified Goodman, which is kind of illustrated here as follows, just illustrating how the equation would be plotted in terms of a Haig diagram, right? Now, there are some important points for us to remember involving the stress life approach for notches. One is that mean stress has more effect in notch parts than in smooth parts. Two, that tensile mean stresses can increase the fatigue notch factor, KF, above the stress concentration factor, KT, which can lead to some fatality in fatigue loading, some failures. Three, that compressive mean stresses can significantly reduce and even eliminate the effect of stress concentrations. And so if we can induce compressive mean stresses, whether it's through shot peening or other processing of the material, we can actually improve the performance of notch parts. And finally, mean stresses inherited in the unloaded part due to residual stresses are often much greater than mean stresses caused by external loading. Now let's do an example, pulling this all together. In this example, we're asked to construct the stress life lines for a completely reversed loading case. So we have a notch part, completely reversed, similar to what we've already done in the previous example. And case B is to construct lines for loading when the minimum nominal stress, sigma min, is equal to 50 megapascal. So in essence, this is going to be a case where we're going to have mean stress. All right, let's start our solution. First, we'll note the material we're given is this quenched and tempered, hot-rolled ROC 100 steel. We consult the table in the book, table A.2, and we're able to get a bunch of properties, fatigue properties for this material. First, we have the tensile strength, the yield strength. Then we have the sigma F and the sigma and the SY prime. We have the sigma F prime, and we have the B parameter, right? We also, consulting the diagram for this geometry, we see we have a circular hole. We're going to say that the KT for that circular hole is going to give us a KT value of 3, right? And then that the nominal stress within this is going to be equal to both some tensile load plus the bending moment that's caused by the position of loading, and we'll end up with a calculation for the nominal stress in this component. For part A, we're going to do the exact same method we did in our last example, where we will we will figure out what our KF parameter is, and then we will apply both the Collins model as well as the Hayward model to approximating those notched curves. In case B, we have two options. One option is to construct the Haig diagram. Now, constructing this diagram takes a couple of points of interest that we would have to figure out, and then we would plot up and over to find our location. A detailed procedure, because this is a very involved procedure, is available in our textbook. Another approach we can use is to apply the more convenient modified Goodman equation. And this is an equation where we're going to assume no yielding. Let's start with taking the equation as we are given it, where we have this KF times SA over SE plus KF times SM over SU. Now let's, based on the information we're given, rearrange this equation. These numerator terms, KFSA and KFSM, those are equivalent to finding the stress amplitude in the notched and the mean stress in the notched components, right? The denominator here, this notched endurance limit of the material, or fatigue strength of the material, that is equivalent as if taking the unnotched and dividing it by our KF factor. And then SU, that's just our ultimate tensile strength. Well, we've rearranged this into this form, and we know the unnotched endurance limit, and we can calculate KF. In fact, we did from part A, right? So we put that in there. We also, we're trying to consider the case where we have some value of mean stress, which is 50 megapascal. If we rearrange SM, the mean stress, we'll find that the mean stress is equal to the stress amplitude and the min. So now we have this equation with only one unknown, the stress amplitude in the notch component. So we go ahead and solve, and we'll find the stress amplitude in the notch component is equal to 129 megapascal. Now that we have that stress amplitude, we can use that information, that modified Goodman equation, where that stress amplitude that we found, that is equivalent to what our endurance limit would be. Now we're going to modify our curve, and now we have a slightly modified curve that incorporates the effect of the notch as well as the effect of that mean stress, right? We could do the same thing with our Haig diagram, where we would find 105 megapascals as the point of interest, and we can see that there is some deviation between the two methods. Ultimately, the more convenient approach, the approach that you would more likely want to use, is to apply the modified Goodman equation. All right, so that concludes our presentation on the stress life approach for notches. I hope that you've enjoyed the video and learned something. In our next video, we're going to learn about how to apply the stress life approach for notches. See you soon.